I'd like to say a few words about the single slit diffraction experiment. In this experiment, you're observing the wave properties of light. So the equipment that you're using, single slit, brings out the wave properties of light in the form of interference. I've set up the laser here so that it's pointing directly into the slit, and the pattern that's being projected onto the screen is a diffraction pattern. I've turned the knob on the left hand side, which you can just see, so that the diffraction pattern is very close to the central peak. The aim of this experiment is to find the wavelength of the light coming out of the laser. When you're actually setting up the equipment, one thing that a lot of people don't realise is that the sensor here, well, actually there's a very small sensor hidden behind this the screen here. The slit here lets in some light, and actually the sensor is small somewhere along the length of the slit. So after you've connected up your multimeter and set it to the correct direct current voltage, DC voltage range, you need to actually move the screen up and down and very, very slowly until you see until you find the maximum reading. What you should do first is to move it from side to side. Let me just do it. Move it from side to side until you get a maximum, and then move the slit up and down to see where the sensor is. You actually have to find the sensor, then screw it in tightly like that when you have the maximum. Let's turn the lights off and turn up the sensitivity on the video camera. Let's see how many lines we'll be able to see. Let's try this. That's really cranking up the sensitivity. The basic procedure in this experiment is to move the screen a known distance away from you and a known distance towards you, and find the positions of the minima, the dark bands. You do that by turning the knob a quarter turn at a time. So you go on one side of the central maximum, you find 3 or 4 or as many minima as you can, dark bands as you can. You come back to the centre and you find the corresponding dark bands on the other side. M equals 1, first order, second order, third order, and so on. You probably can only do 3 dark bands. A quarter of a turn is, well, let me see, there are 1, 2, 3, 4, 5, 6, 7, 8 of these notches on the dial. So a quarter turn is 2 notches. So 1, 2, that's a quarter turn. And a quarter turn means 0.25 millimeters in one direction. I believe it's 0.25. Just check it in your book. I know it's 0.25, I think. check it in your book. So that's 0.25. You look at the voltage that's reading on your multimeter. You write it down. You should see it fall because you're moving away from the central maximum. Another, oops, you do it carefully so you don't move anything. Another 0.25, another quarter turn, another 0.25 millimeters. Another quarter turn, take down the voltage. Another quarter turn, take down the voltage. Another quarter turn, and just keep going until it looks like the diffraction pattern isn't changing the voltage very much. As you scan across the diffraction pattern, the voltage doesn't change on the voltmeter. And then come back to the centre. Oops, I went a bit too far. Come back to the centre and do exactly the same thing on the other side. So again, repeating a quarter turn, just 2 notches, take down the voltage, another 2 notches, take down the voltage, another 2 notches, take down the voltage. If you're near a minimum, if you're near a dark band, it might pay you to be a little bit finer than 2 notches, maybe just do 1 notch when you're near the minimum. You want to locate the minimum as accurately as possible. You want to have an accurate as possible number to put into the formula for single slit diffraction. After you have the positions of the minima, again you will find you'll get the okay. After you have the positions of the minima, you know the distance in this direction. Let's say the distance to the first minimum is y. You know the distance from the slit to the screen. Well, the trigonometry says that if this is here's a right triangle, here's one side of a right triangle, and then the line joining the screen to the slit is another side of the triangle. Well, tan theta, theta being the angle, say, to the first minimum, to the first dark fringe, is y divided by the distance to the screen from the slit. Now, because the distance between the screen and slit is so large, tan theta is approximately equal to theta, and it turns out that actually sine theta is almost equal to theta. So sine theta is almost the same as tan theta. And sine theta is what you want to put into the formula for single slit diffraction. So sine theta is approximately this distance, y, the distance from the centre to the first dark fringe, or the second dark fringe, whichever one you're measuring, y divided by the distance from the screen to the slit. You should be able to get the wavelength to within a few nanometers. So again, this experiment using pretty simple equipment can get you accuracy to within a few nanometers, to within 2 or 3 times 10 to the minus 9 meters. By the way, you will need to know the slit width, and the slit width is written on the slit somewhere. It's either written in an easily visible pen, or it's scratched on somewhere. This one, with this one, the slit width is scratched on here. You can see it if you put it at the correct angle, and it's the numbers 220. fact, this one is 220.9. 220.9 what? Well, if you think about it, 220.9, is it millimeters? No, obviously not. Is it nanometers? No, because 220 nanometers is so small that you would not be able to see this gap. It's 220.9 micrometers, 10 to the minus 6. So make sure you put whatever number you find on your slit width, for your slit width, make sure you use the right units. It's micrometers, 10 to the minus 6 meters. The last thing I want to say is with regards to the batteries. Of course, with so many students using this equipment, you might find that the voltage you get out of that the power you get out of the laser is not very much. After you've checked that the laser, the diffraction pattern is actually, the central maximum is actually shining directly onto the small light detector, the light diode. You set the diode at the right height. If you still get a very small voltage, or apparently small voltage, then you check the multimeter. Make sure you've put the multimeter on the right scale. Now this is off. See, there's a bit that goes, that there's a sort of a notch there. That's off. The scale, well, what scale do you want? First of all, you want DC volts. That's DC volts. That's AC volts. There's a little wavy line there. So you're looking at a peak of about, let me just focus. You're looking at a peak of about 340, 350 millivolts. So you've got to put it on not the 200 millivolt scale, because on a 200 millivolt scale you can't see more than 200 millivolts. But put it on a 2000 millivolt scale. That's the correct scale. Once you have it under the 2000 millivolt scale, and you've made sure that the detector is at the right height by turning that knob there. Then, and if you can't get a good, can't get more than 300, you only get about 200, and that could be a sign that the battery of the laser is kaput, and just ask Joe for another one, or ask your demonstrator, sorry. Don't ask Joe, ask your demonstrator. Lastly, the other battery, of course the multimeters, have batteries as well that fail every now and then because of the use they get in the first year labs. After putting in the black plug into the common terminal, and the red plug into the 10 volts omega milliamps jack in there, stick it in there. Once you've done that and you made sure that you're on the right scale and you're not reading much, then maybe the battery of the multimeter is gone. Tell your demonstrator and he'll get you another multimeter. I just wanted to say a few things about the single slit diffraction experiment. I'm not going to go into it in detail. I just wanted to make a few of the main points. If you have any questions, just put them up on the WebCT discussion forum and somebody will answer them soon enough.